All right, 66. Which energy transitions in singly ionized helium yield photons in the wavelength of 450 to 500 nanometers? All right, so the equation, it's in your book, it's equation 7-41, says that the ionization energy, or the energy of a certain state of a hydrogen atom is equal to Z squared times negative 13.6 EV over N squared. This here is the atomic number, and then this is the, state. And then the other equation that's useful for this problem is converting sort of the change in energy levels from one state to another to wavelength, and we've used this one many times. The wavelength is equal to 1240 EV over delta E. Okay, so we're going to use those two. First thing that we need to do, though, is figure out the energy levels for this helium atom all the way up to N9, the ninth state. Because that's sort of the most that it can have. So you're just going to repeat this over and over and over. So E1, the atomic number for helium is 2, so it'd be 2 squared times negative 13.6 over 1 squared. Let me get my calculator here. So you get 4 times negative 13.6, because this is always going to be the same. So I'll just leave it at 54.4 over 1 equals, obviously, 54.4 EV. That's E1. What about E2? Well, E2 is going to be negative 54.4 over 2 squared. So gives me negative 13.6 EV. E3, negative 54.4 over 3 squared. So over 9 gives us negative 6.04 EV. Doing it again. So it'll be negative 54.4 over 4 squared. So this times over 16. So you get negative 3.4 EV. Halfway done here. So now it's over 25. Negative 2.18 EV. 6. So now it's over 36. E7. So now it's over 49. 2 more here. Now it's over 64. 0.85 EV. And last but not least, 54.4 over 9 squared. So now I put it over 81. Okay. Now, once we've gone through all 9 of them, what we want to do is figure out what is the energy drop or change in the state that will give us a wavelength of 450 to 500. So what I'm going to do here, I'll call this part B, I suppose. If we take that second equation, delta E is equal to 1240 over lambda. So to get a wavelength of 450 nanometers, which is the low end here, we'll need an energy drop of 2.76 EV. To get an energy, to get a a wavelength of 500 nanometers, the upper limit, we need an energy drop of 2.48 eV. So what we want to do then is try and figure out which transitions would have an energy difference between these two numbers here. So for example, if you look at the energy drop from 1 to 2, or I suppose from 2 to 1, you went from negative 13, you went from negative 13.6 to negative 54.4. So 54.4 and 13.6. That's a difference of 40.8. That does not fall within that range. So that's not a good difference. What about, so we need to find something that's falling between 2.5. That will sort of look. So 3 to 2, no, doesn't look good. 3 to 4. That might be close. Let's do it. So 6.04 minus 3.4. 2.64. Okay, so if we look at this one, so if we look at the energy difference from E4 to E3, we get negative 3.4 minus negative 6.04. That gives us an energy difference of 2.64 eV. That does fall within the range of these two. So this transition will result in a wavelength between these two. Let's figure out exactly what wavelength that is. So now we go to wavelength is equal to 1240 over delta E, which in this case is 2.64. That will give us a wavelength of 469.7 nanometers. So that's one of them. That's the transition from n equal to 4 to 3. Let's see if there's any others. So that was 4 to 3. What about 5 to 4? I don't think so. What about 5 to 3? No, that looks too big. All right, what about 6 to 5? No, that doesn't fall within. What about 6 to 4? That one's close. Let's check it. 3.4 minus 1.5, 1.9. Okay, so it doesn't fall within. So let's try 5 to 3. No, that's way too many. All right, so 5 doesn't do it. What about 6? 6 to 5. That doesn't fall between those. What about 6 to 4? That's close. That's literally what I just did, Chris. Okay, so so 6 doesn't work. What about 7? 7 to 6? No. 7 to 5? No. 7 to 4? Maybe. 3.4 minus 1.1. Oops, 3.4 minus 1.1 gives me 2.3. That's under our lower limit, so that doesn't work. And then if I do 7 to 3, that's way too many. Okay, so 7 doesn't do it either. What about 8? 8 to 7? No. What about 8 to 6? No. 8 to 5? No. 8 to 4, though. 3.4 minus 0.85. 2.55. That does fall within. So this is our second one. Oops. So delta E is equal to E8 minus E4. The difference of those is going to be negative 0.85 minus negative 3.4. That'll give us a change in energy of positive 2.55 eV. So let's figure out what wavelength that will produce. 2.55. So 1240 divided by 2.55 gives us a wavelength of 486.3 nanometers. So that one is from n equal 8 to 4. So if you drop that transition from 8th level to 4th state, it will produce a photon with the wavelength within the range. Okay, so we're almost done. We did 8, so now we just got to look at 9. 9 to 8, definitely not. 9 to 7, definitely not. 9 to 6, definitely not. 9 to 5, no. 9 to 4, let's check those two. So 3.4 minus 0.67, 2.73. Oh, okay, that is within our range here. So let's do that. That has to be our last one, right? So let's do it down here. Delta E is equal to E9 minus, what did I say, E4? E4. So E9 is negative 0.67 minus negative 3.4. You get a positive 2.73 EV. Therefore, if we look at our wavelength here, it's going to be 1240 over 2.73, which gives us 454 nanometers, also within our range. That's from n equal 9 to 4. All right, so those are all, that's